Hello and welcome back. I was going to continue the video on the work I've been doing on the Eico 443 semiconductor curve tracer. I have managed to replace capacitors, and also the one of my main concerns was when I was originally testing it, the two sockets for the transistors, for the signal transistors, they were basically not making contact with anything. I mean, I couldn't even get a transistor to plug in there well and feel like it was heating, much less get a good installation on it. I managed to actually find some new sockets of exactly the same size and format on eBay. The only difference there is they are a different color. The original ones are black. These are brown, as you can see, but they make an excellent contact with plugging in a signal transistor, and they are exactly the same configuration of solder mounts and everything. And I did do some testing on them, but I'll go over the functionality on it with you in a bit. But I was going to go over just a quick overview of what I did do inside the back of the unit. I should depower it for now. Just as giving a view. That was the only really thing I had to do on the top side of the unit. On the bottom, I ended up replacing most every out of value component and some of the older capacitors. As you see, I've got some sprayed gargange drops in here and some new, there's two electrolytics, one's behind another orange drop, and there was some other resistor components I had to replace on the switch decks. But other than that, the soldering for the replacements on the transistor sockets came out well. I got to reuse the original wiring, and I did clean up all the potentiometers, put some D5 on this one as well for a little bit for lubricant. Curiously enough, this one rheostat, I've actually found that exact part still available for some reason. They're about 20 or 25 bucks a piece, so I suppose if somebody did have a failure on it. The bottom line on this piece of equipment is none of it is really what you would consider a calibrated laboratory grade piece of equipment. It's a handy bench item for a tech to use to troubleshoot and figure out whether you've got some faulty discrete components as far as diodes or transistors, and also you can check the breakdown voltage on diodes, which is one of the first things I'm going to do going over things. One thing I was going to do first is go over part of the calibration on the unit from the manual. It's got one spot that needs to be calibrated. I'm going to go with that. Let me get a screen record going here so I can get the manual going. We're going to go up to the initial calibration on the unit. I'm going to find it in a second here. Here we go. Instrument calibration. We're going to zoom in on this as much as we can here. The VTVM, I'm going to use a digital voltmeter. It's about the same. So we've got AC power. We're going to leave that off for right now. I'm going to take a digital voltmeter instead of the recommended VTVM, which I do have one, but it's not in probably a calibrated, what you'd consider a calibrated working state, so we're going to just use something different. It says power it on, rotate voltage adjust control fully counterclockwise. I can power it back up. And power's off here. I'm going to turn on my Isolation transformer, which also turns on my scope, but that's fine. Power it on. Rotate the voltage adjust control, which is this one, fully counterclockwise. Connect AC line cord. Position power switch on, off switch to on. Position high voltage test cal switch to cal. So that's this one right here. Connect the VTVM to vertical binding post and ground on rear of the curve tracer. Now on this one, the vertical output is going to be on the left side here. So we're going to take a couple of test clips just to hold the end of the bananas, just to hold the leads. And connect them to the digital voltmeter. And according to the digital voltmeter, what we have is a 1.67 volts. And it says we're supposed to have 1.7. So it says if you don't have the proper voltage, you need to adjust R6. And R6 is that one right there. Now, I tried adjusting it. I'll try adjusting it again, but it's an old potentiometer, and it seems to just have one spot that's worn out right about the 1.7 volt position. Apparently somebody might have been trying to tweak it too many times. Today it feels a little better maybe. We're getting it. Okay, well, considering that I haven't had any warm-up time on the unit, if you can see, as you can see, it's got a good 1.7 volt reading on it now, so it's better than it was, I suppose. But last time I did check it, I had a hard time really getting that guy into good position. So that's AC volts 1.7. So we're going to break down the meter and get it out of the way. Turn the power off on the unit. And then after that, you've got the oscilloscope connections, vertical and horizontal. The one thing you need to pay attention to is I did get some adapters to go from a BNC to a banana, and the one thing you really have to be aware of on these is on your connections you have on these particular ones, some of them are colored, which makes it easier because you've got a red on your signal side and a little black on your ground along with that. This one just has that little tab is going to indicate your shield ground on your connection. So when you do connect up to this, you want to make sure that you have both. My ground positions are both facing on the outside of the outside connections of the unit. So that's what we're going to do. We're going to plug in corresponding cables to those two connections. Tidy things up a little bit. I've got this connected to what wouldn't be the best choice of oscilloscopes, but it's the smallest one I have as far as bench size. It also has a chance of fitting into the shot through the screen, and I can adjust the camera fairly easily to pick up a difference on it. So we've got that part of it going on, and then after that we have to go through some calibration functions. Now we've got the rectifier PIV calibration. So slide power switch on, off to on. Well, I've got the scope set up in XY mode. I have it currently set to 1 volt vertical, 1 volt horizontal positions. The thing about this particular scope is it limits the size of the sweep on the signal to about 10 centimeters wide by 8 centimeters high, so it's not for your two axis inputs. So it's not necessarily going to calibrate properly, because part of the calibration is basically it wants you to set up the test signal so it gives a 5x5 or a 10x10 45-degree horizontal, and in this case I cannot do that. I am going to calibrate the scope as well as I can to get it to a proportionate display, but I won't be able to do a 10x10 in any way, shape, or means. What I figured the best I could do is a 5x5, and now you would think that that would be doubling the signal value on everything, but the one odd thing I found is that it really doesn't, because it's going to take, the scope is basically set at a 1 volt per division on the vertical and horizontal axis, and the voltage it's picking up is actually it's actually true voltage, and B, it's picking up what is subjected or what's connected to the actual component under test, which would be the diodes. So at the point of measuring the diode function on this, we're just going to go with, if it has a 1 volt horizontal deflection, 1 centimeter horizontal deflection, that means that the voltage that is applied to the component is 1 volt. So we're going to try to prove that, I guess, and the best way to do it would be to hook up a common diode to it. I've got a 1N4007. It's supposed to be a breakdown voltage of 1000 volts in reverse. In this case, I'm just going to go right to the test position here. Now, what happens when you're in the test position on this particular unit is if it starts to show conductance, it will take the trace and deflect it into a vertical configuration. And you can look at the oscilloscope itself. I'm slowly turning up the voltage. And I've gotten to about 0.6 of a volt, and you can see where it's starting to show the diode conducting. Turned it back down, and I found that I can get a little better accuracy out of that if I take my horizontal and set it to 100 millivolts per centimeter. See, it's about 600 millivolts, and right at 600 millivolts it starts to show 600 or 700. It's starting to show that diode conducting in the forward current direction. I'm going to take another similar diode. This is a pull out of a older audio amplifier, a Eico ST120. And this one shows it's starting to conduct a little earlier than that one, but it's showing the same properties. So this is the forward direction. This will show that A, it's functioning as a diode, and B, it shows the actual breakdown voltage of the forward conductance end of the diode. Now what we're going to do for these guys now is we're going to set this back to 1 volt per division, and we're going to change the ballpark a little bit, because what we're going to do is go to the reverse breakdown test. So in this case, what happens is now the tester is trying to find out what voltage needs to be applied to the diode in order for it to show breakdown conductance. And in this case, we have to change some switches on the unit. I have to change this one from forward to reverse. This switch now comes into play because it lets you range through the how many volts per division, and in this case it starts to follow the calibration as far as the deflection per volt. Now, since the instruction screen was showing that 10 by 10 square and it's halved, that would mean that each centimeter is now twice the value of what the switch is set at. So in this case, if I'm set at 1 volt, that's actually 2 volts for its deflection. And there's also one more thing about this guy. It's got, once I'm in the high voltage direction, it's got an indicator light here that's supposed to flash. It's a neon light. It's basically a relaxation circuit oscillator where it lets the voltage to the light get pulled up to a certain voltage. The light conducts, flashes on, and then it discharges the circuit, and then it has to cycle over and over again. There's something wrong with the values on the oscillator, the resistor, the capacitor. They're all new components, they're all within spec, but somehow or other it's still not working, so it could even be the bulb. So I'm going to have to tinker with that. That'll be a later part of the video. So, but I do know that at this point, these leads are capable of pulling out over 1400 volts AC, because that's what that transformer inside the unit had. Plus it goes through a diode, and I'm not sure how well it's converted to DC, but I think it might be just pulsed AC or pulsed DC. I'm not sure, but I haven't gotten down to anything I could look at the waveform with, because anything I connect to it also disturbs the signal going back to the scope. So I'm not going to concern myself with that too much as its functionality right now. So in this case, we're going to check the breakdown voltage of this diode. Now keep in mind that and then also another safety feature of this unit is you have to press this PIV test button. So that makes you always have one hand on this no matter what's going on in order to get the voltage out of it. So it's hard to create a circuit through both of your hands, which is usually fairly dangerous. In this case, what turning up the voltage is causing a negative deflection on here, which is kind of a pain in the ass because it doesn't let you read things right. I am going to have to take the scope setting on the Y channel. I have it off. I have the inversion off. I'm going to turn it on. So what that should do is make my deflection, once I find my, oh boy, I'm going to find my cursor again. Oh, there it is. Okay, they're both on. And use off. There we go. So we got a positive deflection there. So we're going to up our ranges here, and what happens is we're at 100 volts per division on this. Let me zoom on the scope a little bit. So as we're applying voltage to it, at 100 volts per division, keeping in mind that normally this meter would be a 5 by 5 diagonal for its calibration deflection. We have, or a 10 by 10 centimeter, we have a 5 by 5, so that would mean that each centimeter is going to be double its voltage. If the switch on the volts per division is set at 100 volts on the Eico, that would mean that we're subjecting it to 200 volts. So right now we're at 1 centimeter, which is 200 volts. We're at 2 centimeters, which is 400, and at the 1 microamp, current through the diode, we can see that we're starting to break down at a little over 400 volts on this particular diode. So this diode was basically tasked with rectifying AC voltage for that was configured as a full wave bridge, one of 4 diodes and a full wave bridge for a power supply for a Dynaco stereo ST120 solid state amplifier. So in this case, it would, it probably could be rated a little better as far as current, but that was also another item that was built to a price point for parts. So that's for getting 1 microamp through the diode. Now if I change the switch up, I have 3 settings on this. I have 1, 10, and 100 microamps. So on the 10 microamps, in order to get that, if you notice, there's just a little bit higher amount of voltage needed. It's about the 425, 450 range. Now if we try to get 100 microamps through that diode junction in reverse voltage, it's going to take even a little more. So basically for each setting I have, that's the 100, that's the 10. If I go down to 10 microamps and then change the switch to 1, notice it picks up the fact that there's 1 microamp of current sneaking through that junction. But if we push it to 10, it's taking a little bit, it's providing a little more resistance because it's not fully broken down for that much current at that voltage. But if we put it up to 100 microamps, and you got to apply a little more voltage to it in order to get that junction to break down and flow more current through it. So that's an interesting tester. It's a quick tester to be able to check the functionality out. You can probably also apply the testing to Zener diodes up to a certain point in voltage. You can, depending on how you want to manipulate them. There's an interesting diode I have. Oh, that first diode, by the way, I pulled, that was out of a CFL light bulb printed circuit board. So it's kind of no surprise to use a better diode on that one. I have an interesting diode here. It's a DB3, which is the bidirectional diode. It's also another pull out of one of those lights. Basically, this diode was made to conduct in a higher voltage in both directions. One a little more than the other one. So this one ought to be interesting. It's a high enough voltage. I think one side is 30 and the other side is 35. So it's a high enough voltage where it won't break down on the normal forward setting under either one. So we're going to have to test them both in the peak inverse volts position. So we're going to go in the 10 microamp setting and see how things go. And if you see at this one, I've got 10 volts per division. Let me get back on the scope again. So that's breaking down at about 35 volts once it hits the conductance on it. If I raise it to 100 microamps, it's about the same. See if I can get it to behave any differently between 10 and 1 by just holding my finger on that rheostat. It's not the rheostat's definitely not a fine-tuned. Yeah, it shows a little more going through to 10 than 100. It's behaving properly. But if I just switch this unit over to the forward direction, it would not show the conducting on it. So we're going to just have to physically reverse the connection on the diode. So I've done that, and then in this case we're going to go back to testing it again. And it tests about the same. It's made to conduct voltage in both directions. Like I said, I think the specs on this particular one, this BD2 is about 30 or 32 in one direction and 35 in the other. They use it as part of the starter circuit in this compact fluorescent light electronics board. It's one of the white blobs on the screw and bases that you used to see on the bottoms of those bulbs. They're chock full of some little parts that the parts usually don't go bad before the bulb does, so you can actually get in there and harvest yourself some cheap parts as far as resistors and transistors and a few diodes. So this part of the tester actually is functioning properly, and interestingly enough, it's behaving itself. So we're going to remove our diodes from there. And we're going to go on with playing with some transistor stuff. So the transistor calibration is a bit different. We have to go, it wants to see 5 centimeters horizontal and, no, I'm sorry, yeah, 5 centimeters horizontal and only 8 vertical. So this scope can actually do that. So in order to do that, though, I have to go over to the transistor function, and I have to set my meter up accordingly. There's a test switch here that I have to set this to, and I'm going to have to go through a bunch of adjusting here. A-B calibration test. Oh, calibration, here we go. I got to be in a calibration position. That's where my problem arises. I'm going to go the opposite angle of what this tells me because it's also inherently backwards on the sweep. You'll see that as I come up to doing things. So I got to go to NPN as well. Most of the transistors I have for now are NPNs. And this scope is a royal pain in the ass to get things set up well on it. Whoops, here we go. I gotta go. If the trace goes off screen, it kind of tells you it goes off screen by flattening out that part of the trace, but it's awful weird. Gotta go into fine tuning this guy here. And let's see, we've got 1, 2, 3, 4. We've got 4. So there basically we have 5 by 8 on the scope and the calibration. So now in the test position, I'm going to take I forgot if these are they're either 3904s or 2222s. They're a common NPN. Got position A. At this point in the video, I had some technical difficulties involving me trying to test a signal transistor in a socket that was improperly installed into the socket, and I wasted about 5 minutes of my time. So in order not to pass that 5 minutes of a time waster on, I edited that part out and continued with a properly installed signal transistor to go over the functionality of the curve tracing on transistors in the unit. Anyways, I'm going to try to substitute another transistor in here. I figured it out. I had my transistor oriented wrong. I had it, instead of going emitter-based collector, or collector-based emitter, I had the transistor turned around the wrong way. So now it's behaving, the sweep is behaving properly. And in order for you to measure the signal gain according to Okay, I'm back, and I will admit I had a little bit of a brain fart setting up this meter for, or this curve tracer for checking transistors. I did put a transistor in here, and I had the connections wrong to the transistor. So we're going to go over things again, doing everything the right way. You don't need to waste your time viewing me waste my time, so because it would be a big collective waste of time at that point. We have the scope set up per the instructions for the calibration. Where are we here? Calibration for PNP power transistors and NPN signal. And zoom in on the screen a little bit on that one. It's going to should look like the figure number 3 on the right, except what I'm going to do is invert my signal on the vertical axis of the scope in order to make it in an upright position, because if I don't, what will happen is you will see the trace come up like figure 10, which means it'll be figure 10's the NPN signal. It'll basically be upside down, so I'm going to configure the scope the right side up that trace. So it's no huge deal. And the one thing about this unit is it is supposed to be calibrated. You have marked values on the signal and the power knobs for what is supposed to be the beta, and according to our steps, for step G, beta adjust, rotate the appropriate beta control signal or power until 8 divisions of the vertical portion are obtained. Position the trace on the oscilloscope until a display is in figure 9, 10, 11, or 12 is shown. Let's switch over to the screen here. So on figure 10 here, it wants you to display from the root of the sweep 8 divisions up to the top of the 4th horizontal sweep, and then it says on step H, it says beta may now be read directly from the beta control. So we're going to check that eventually, but what I'm going to do is going to put a transistor in the proper way, because up until now I had them in backwards, which doesn't work really well. And if you look, we have, I'll zoom in on the trace a little bit here. I'm set to a gain of 500 on the knob. So what this does is it's kind of counterintuitive, because the lower voltage you have, the lower voltage and current you have driving the base of the transistor would result to the higher value on the knob, which is fully clockwise at this point. So as you're going down in voltage, the calibration is actually decreasing the gain values as well that's marked on the unit. So as I go down and I get to the point where my traces, zoom out a little bit. Right now I'm about a 300, and if you notice, on the scope the sweep is actually going upwards in value. And at this point, I am at 8 vertical centimeters of deflection. and my gain on the knob registers just over 125, if you could see it on the pointer. So this isn't, and treating this meter, like I said, this is not in any way, shape, or form a laboratory standard piece of test and evaluation equipment. It's a bench technician's tool to help troubleshoot and get along with trying to find parts that aren't behaving quite properly and trying to eliminate them as part of the process of troubleshooting. Now, another thing about this in the curve tracer function is the drive voltage on the horizontal is a set value, so you're not going to see a large deflection nor any way to really raise that voltage in order to check a transistor to breakdown. What they recommend you do if you want to check the breakdown properties of a transistor is to actually use the diode mode on this unit to plug in your test leads and connect it to your connector to base, emitter to base, and check your, you can go up to a higher voltage function on the inverse voltage position on those, so you can actually check a power transistor and see how it behaves, how the junctions are behaving as far as it reacts to higher voltages. Now, keeping that in mind also, it's not all, this is, although it is an AC signal, it's 60 hertz, it's low frequency, so it's also not going to tell you how it behaves at higher frequencies. Not too many curve tracers do. I think they're all standard going to be working at a lower frequency. So this is, it's basically a quick test tool, but there is one function that this does have nice, is it does have an A-B comparison function to it. Scope timed out. If you get down here and look, it's got 2 jacks and it's got an A-B switch, and it would let you plug a second transistor in properly. Whoop! Oh, that one got away from me. Hold on. Oh. Okay. It ain't one thing, it's another. We have the, basically, I think it's the same, it's either the same model or you might have a 2222 and one and a 3904. They're both NPN signal transistors. Right now I have the switch set to the A selection, and I just changed it to B, and I don't know if you noticed on the scope, I can zoom in on the scope again, but there is a slight difference in gain on these. So this is the B position. This is the A. So if you notice in the A, it's just a slight little bit more gain in that transistor. So this would give a fairly quick way of matching them. It's not an exact match as some other people have come up with test jigs to do that, but if it's something that's not really critical, but you need to find some matched transistors, that would be a good device to use in general, just to check the function and get an idea of the ballpark of the gain. I'm probably going to go into checking the gain function a little better a little later in the video, but for right now I just want to cover one other thing on these. We have, so that's the signal transistor portion. Now this is where we're going to run into what I would call a snafu on this unit so far, is it's not quite behaving well as far as testing power transistors and coming up with a good set of curves on the curve tracer. I have a selection of some older pulls I'm going to go through here, and I've got one. Here we go. This is an old. This has the part number marked on it from the. It's a Motorola part, but it's got a MJ802 and an 84 transistor. I'm not exactly sure what part this is, but we're gonna stick it in here and see how it behaves. It does have a fairly nice enough built-in socket to test TO3s. So we're going to put it into A. And as you see, we do have a sweep on the scope. I think I checked this with another meter and marked about a 57 for a gain on it. Now, granted, this is the NPN, and I tested it with one of the all-purpose testers there. I think I got a 57 on it in that. On this one, the signal knob is set about 70. It's ballpark. I could actually, I have another probably comparable transistor I can. Oh, I've got this one gained out at 179, so we're going to see how this behaves. I'll give it a B. Oh, and lo and behold, it was a lot larger. A lot better in gain, so this one gains out to about 130, but as you can see, there's no way, shape, or form are these two matched. Now, there is one thing that I'm going to go into a little later on this unit. It makes a claim that on the sweep, the horizontal sweep drive voltages on the staircase, that the voltages are supposed to be basically in a linear progression, so it would help you to indicate finding a transistor that has a lower gain at a lower base voltage current, because it just might behave a little differently for some reason of either the transistor's design or the fact that it might be faulty. And in this case, I'm going to question that a bit later. I'm going to look into something later, because in order for that to be an accurate statement, you would figure that you would have to have accurate progression on your stair-step voltages, and it really doesn't. I'll go into that later and I'll show on it, but there's also another fault on this one. Now, these are basically power transistors, and in this unit you are supposed to be able to drive transistors a little harder. Now, right now these aren't being driven very hard. There's most curve tracers, when you set them up to test power transistors, you will actually feel the transistor is getting a little warm to the touch. These have nothing. So what I can do is I can set the switch over to the power side, and a lot of things change. Now, it's almost like it wants me to recalibrate, so we're going to do that. It also wanted to see a 5x5 deflection, and it threw the whole positioning of the trace off off the meter severely here, so I've got to reset all of that. And that threw everything off. Okay, we've got an 8x4 there. Okay, we've got an 8x5. So we're going to go for it. And right now I think we're totally inverted. Oh, my gain. Okay. I use a different gain knob in this. Now here's where we have a different quirk on this guy here. We're gonna go inverted on channel 1 again, I think. Or if I can, this is channel 2. Take the invert off. Menu off. Now we gotta reposition. This XY stuff is a pain in the ass. There we go. Now here's one of the flaws I was talking about. At this point, this meter is only creating one staircase step instead of 4. That's all I get. If you notice on any of the other ones, you would see the trace going up and going up to the next step, next step, next step, until you got all 4. In this case, we only have 1, which is kind of strange. And my beta setting on here is also very far off for the power setting, but I can also, at this point, I can also feel the transistor in the A socket getting a bit warm. So this one's supposed to have probably lower gain than what it's testing, but you got to consider too that it is driving this transistor a little harder than even the checker I was using, or the meter, or this tester in the signal position. So we're going to switch this from A to B. We know that the transistor in the B socket has more gain, and sure enough, it will take a, supposed to have more, but actually this is now working intuitively. As I turn the knob down, the gain value goes down. Or is that the same as the other way? I'm not sure. Anyways, this one is saying that that second transistor in the B socket has less gain than the one in the A socket. And that may be true on the level that it's being driven at. The only way to test this out, and I'll probably do it later, it would be to interrupt the connections to the transistor and insert an ammeter and do the math, which I'm probably going to do as part of this video. For right now, I'm going to leave it at this. I'm going to work on doing those connections and make another part video with some more of that information. So basically, you have the unit. It's in some sort of functioning condition. I'm not sure how correct it is, but I'm going to get more into detail, into troubleshooting, and seeing what I could do to make the factory unit behave like it's supposed to without any major drastic modifications. The other unit I have that is the kit built unit, I'm going to try to restore that one as well as I can to the kit instruction, directions, and wiring, and see if it behaves the same as this one, because I've got a very limited amount of information on this unit. I do have the online access to the manual, the factory user manual on this. It has a schematic, but the factory schematic unfortunately does not have any values on it for voltages. and it's also kind of hodgepodge together. I took the time to put all 3 sheets onto of the factory schematic onto one bigger JPEG or bitmap, I forgot what, and I went through, cleaned it up as well as I could, cleaned up the connections, all the values I can find on things, and I'm going to plan to put some notes on it. And I also made a smaller schematic excuse me, condensed, with some of the wiring positions that just concern the circuitry for powering the curve tracer function and getting the signal to the transistors and then to the oscilloscope as well. Made a smaller sectionalized copy of those, broke it down, and I'm going to probably record some voltages on that as far as any static DC voltages I can find off the unit. Check some signaling on it and go over signaling on the next part video as well, and see how I can pick my way through the breadcrumbs in all of this. And one option I'm going to possibly explore on my reconstructing the kit-built 443, since it basically does have a little bit less of a resale value per se and historical value as well, since it's a kit and it's already built and it's damaged. It's going to get some repair to it, but it's missing all the shiny knob parts on the top of the unit, and it's missing all the caps on these guys. And I might actually rebuild that thing using discrete component circuitry to get it to behave properly and functionally like it's supposed to the best of my ability. It's possible to build a staircase generator I found off of a schematic that I found online using just transistors and capacitors and resistors, and I'm interested in seeing how that'll function. I'll probably even jig up a breadboarded version of it just to test and see how it behaves. So I'm going to leave this video with that, and I do thank you for watching, and stay tuned for further exploration on the troubleshooting, calibration, and repair of this unit. This content is available on YouTube and Odyssey.com. If you enjoyed this, please like and subscribe. Hope you return soon.